Great, guys. So in question 2, this is usually sequences and series, starting with a straight line equation and then some sort of geometric pattern. So question 2.1, the first 3 terms of an arithmetic pattern are -5, 2, and 9. So 2.1.1, write down the next 2 terms of the pattern. Arithmetic means there's a constant difference. So -5, 2, and 9, the constant difference. This guy goes up by 7. This guy goes up by 7. So another 7 will take us to 16, and another 7, 23. So the next 2 terms in the pattern are 16 and 23. We can write it T4 equals 16 and T5 equals 23. So the 2.1.2 showed that the sum of the first n terms of this pattern is given by this. Okay, so this is our Sn. So our formula here for our series is this guy up top for an arithmetic. This guy over here is for geometric, that is not to infinity, and this guy here is later for our series all the way up to infinity. So Sn equals n over 2, and then I'm just going to write this guy down so long. So what we need to do is plug in our a. Our a value is the first term in this pattern. It is the -5. So I'm just going to change the form here already to make it 1 over 2n, because that's how they have it set up. And then 2 times -5 plus n minus 1 we leave as is, and then our difference is the 7 over here. That is our difference. So I'm just going to keep working up here. So 1 over 2n is what we have here. 2 times -5 is -10, and then we have plus 7n and then -7 if I foiled this 7 into both of them over there. And then this equals 1 over 2n, 7n, and -10 minus 7 is -17, and that is what they had here as well. So 2.2, the first 4 terms of a quadratic pattern are this. So a quadratic pattern has a constant second difference, not a constant first difference. So they love this question. 2.2.1, determine the values of x, 3 marks. So we have x, 3x minus 5. We have 4x minus 3. And we have 5x plus 1. So these are the first 4 terms. What we know is that they have a constant second difference. So what we need to do is go this term minus that term. So we have 3x minus 5 minus x is the value gap over here in order to bridge from x to 3x minus 5. Then we're going to go 4x minus 3 minus 3x minus 5. So 4x minus 3 minus 3x minus 5. I've just distributed the minus in one go. And then this last guy over here is 5x plus 1 minus 4x minus 3. So that is going to go 5x plus 1 minus 4x minus 3 is positive 3. So I am going to simplify this a bit before I do the second difference. So 3x minus 5 minus x. So 3x minus x is 2x minus 5. 4x minus 3x is x. Minus 3 plus 5 is plus 2. 5x minus 4 is x, and then plus 1 plus 3 is plus 4. So what we have, these are our first differences, and we need the second difference, because what we know about a quadratic is that the second differences are equal. So we're going to minus them again. X plus 2 minus 2x minus 5 is plus 5, and x plus 4 minus x minus positive 2. So I'm going to simplify these guys, bring them down, and then solve for x. So x minus 2 is minus x, plus 2 plus 5 is plus 7, equals x minus x is 0, 4 minus 2 is 2. Then I'm going to take my x over, and my 2 over, x equals 5. So by that, we did our first difference. This was our second difference, and then we equated them, because what we know about a quadratic equation is that the second differences are equal. Great. So at this stage, x equals 5. We've just solved that. So 2.2.2, if the pattern continues indefinitely, prove that all the terms of the pattern are positive. So this guy is x. So we're going to plug 5 in wherever x used to live, so we can figure out what pattern we're dealing with, and we can do our normal setup for a quadratic number pattern. So x equals 5. So 5 is the first one, is 10, is 17, is 26. So we have our first 4 terms. As we work here, we'll have a first difference that is different. This guy is 5, this guy is 7, and this guy should be 9. And then what we have is a constant second difference where it goes up by 2 each time. So the way that we check this out is 2a equals 2, 3a plus b equals 5 in this case, whatever this first differences, and then a plus b plus c equals 5 here as well. So we can go ahead and solve for it. A equals 1 over here. Then we bring this a into the next pattern. So 3 times 1 plus b equals 5. Take that over. 5 minus 3 is 2. B equals 2. And then we plug in our a value, which is 1, our b value, which is 2, plus c equals 5 to solve for c. Therefore, c equals 2. This stage, we have the number pattern, which is n squared plus 2n plus 2. Great. So they're asking if the pattern continues indefinitely, prove that all the terms of the pattern are positive. So it is kind of hard to interpret that at this stage. We could obviously plug in different values and see if this works for every value that is negative or positive, because this is a parabola. But what is an easier way to treat it is to split up this 2, because then we have n squared plus 2n plus 1 plus 1. And then this whole grouping over here is something we can turn into a bracket, because if we were to factorize this, it is the same as writing n plus 1 squared. N squared, n times 1 is n, times 2 is plus 2n, 1 times 1 is positive 1. And then we have this positive 1 out here. It's like completing the square. So at this stage, what makes it a lot easier to interpret here is that n plus 1 squared, our n is in a bracket that gets squared, which means regardless of whatever value we've plugged in, if it is negative or positive, if we end up squaring that n value, it results in a value that is positive, which means we just say, therefore, all values are positive. So question 2.3, it is saying consider the geometric series. So 2.311, it says determine the values of p for which the series converges. So when we are dealing with something converging, it means we are dealing with this formula, a sum to infinity. As we'll see in 2.3.2, if the sum to infinity of the series is 1, determine the value of p. But when they are talking about converging, they are talking about this inequality over here. So determine the values of p for which the series converges. We first need to get our ratio. And the way we get a ratio is by taking the second value, dividing it by the first value, and taking the third value, dividing it by the second value. So what we need to do is we're going to go 3 over 4 p minus 3 squared, because this is t2 over t1 equals t3 over t2. So t2 is 3 over 4p minus 3 squared over 1 over 2p minus 3. So right here, what we have is this guy is gone and this whole guy is gone because they simplify. And then we have 3 over 4 and 1 over 2. So I'm just going to simplify that. And that equals 3 over 2. So what we have is 3 over 2p minus 3. And if we have it on this side, we'll see if we do it the same on t3 over t2, it'll end up being the same value because our ratio is constant. So our ratio is constant. So at this stage, they're asking determine the values of p for which the series converges. So we have 3 over 2 p minus 3. That is our r. That is the ratio. This is what this whole thing helped us solve, is that there's a constant ratio as we move from one to the next. So what we're going to do is we're going to plug it into this inequality. We have 3 over 2 p minus 3 over here. So what we need to do is we need to solve for this guy. And what we do to one side, we do to all sides. So we times it up by 2. We have minus 2 over here. We have 3 p minus 3 over here. And then this guy is times by 2. So at this stage, we can divide by 3 here. So we have minus 2 over 3 equals p minus 3. I'm dropping the brackets. And then this guy is 2 over 3. And then last move is that we have to move the 3 to both sides. So minus 2 over 3 plus 3 is 7 over 3. And then we have p here. And then 2 over 3 plus 3 is 11 over 3. And then we have solved for the values for p to satisfy this equation. So then 2.3.2, it's saying if the sum to infinity of the series is 1, determine the value of p. So 3 marks. So the sum to infinity of the series is 1. So they're giving us the actual value of this sum to infinity. So what we need to do is we need to plug p into this formula to then solve for it, because we have the ratio, we solved for that in terms of p, and we have the a value, which is given to us in terms of p. So I'm going to rewrite this formula down below, and then we can solve it. So we have s infinity equals a over 1 minus r. So they told us that the S infinity equals 1. So we have that over there. And then the A value is this guy over here. It's our first term in the sequence. So if we plug that in, we have 1 over 2 P minus 3 over 1 minus r. A reminder that r was over here. That's what we solved for in the previous equation to figure out the convergence of it, or the values for which it converges. So then we're going to plug this in here. 3 over 2 P minus 3. So we have A, we have R, we have the sum to infinity. They told us that. And now we need to solve for P in this equation. So we have 1 equals 1 over 2, or we can just call that P over 2 minus 3 over 2. 1 minus 3P over 2 minus 9 over 2. So at this stage, we are then going to say 1 equals P over 2 minus 3 over 2. At the bottom here, we have 1 minus 3P over 2 minus minus, so it's positive 9 over 2. So 1 equals P over 2 minus 3 over 2. And then at the bottom, we have 1 plus 9 over 2 is 11 over 2 minus 3P over 2. We have 1 equals P minus 3 over 2 over 11 minus 3P over 2. So what's going to happen here is I can tip and times this, or I can times this whole thing up there. So we have 11 minus 3P over 2 equals P minus 3 over 2. So they're both over 2, so we can drop that. So we have 11 minus 3P equals P minus 3. Take the biggest negative P over to that side, so that becomes 4P. And this negative 3, take it over there, it becomes a positive 3, is 14. And then P equals 14 over 4. Simplified is 7 over 2. P equals 7 over 2. Great job, guys. So that is question 2 of the June 2025 paper. Let me know if there are any questions in the comments, and then I will get back to you on that and see you in the next video.